In the last lecture, we have learned about quasi-convex subgroups. In this lecture, we'll prove that centralizer of a hyperbolic group is a quasi-convex subgroup. So let us begin with this lemma, which states the following. So let G be a hyperbolic group. So therefore, it will be a finitely generated group. Let us take S to be a finite generating set of that group G. And now suppose let us take two words U and B in the free group generated by S. And suppose these two elements U and B, it represents conjugate elements in the group G. So then the claim is there exists an element X in this group G such that so X inverse Ux is equal to B, and the distance between 1x, so this distance in the group G, so this distance between 1 and x, so this is less than equals to mu to the power maximum of the distance between 1 to u and the distance between 1 and b, where this constant mu depends only on the hyperbolicity constant of the group G. So let me again repeat. So we have started with a hyperbolic group G with finite generating set S, and now let us take two elements U and B in the free group generated by S. So this U and P, so this will again represent an element, represent elements in the group G, and suppose they are conjugate in this group G. So then the claim is, so there exists an element X in this group G such that X inverse Ux is equal to B, and distance between 1x is less than equals to mu to the power maximum of the distance between 1u and distance between 1b. So these distances are taken in the group G, and this mu is a constant which depends only on the hyperbolicity constant of this group G. Okay. So what is the proof of this lemma? So we'll be needing the exercise that we have given in the last class. So let G be a delta hyperbolic group. So this means that the Cayley graph of G with respect to S, so that will be a hyperbolic metric space. In fact, that will be a delta hyperbolic metric space. So we have taken two words U and B which are conjugate in G. So this will imply that there exists some element G in this group capital G such that B is equal to G inverse UG. And we have this picture here. So take this identity element, this my element U. So join 1 to U by a geodesic, and let us take this element G and take this element UG and join G and UG by a geodesic in the group G. So what will be the this word representing this geodesic? So this will be exactly equal to G inverse UG, which is nothing but equal to B. So B represents this geodesic joining G and UG. Okay. So now let us take this U to be equal to A1, A2, AM and B to be equal to B1, B2, Bn. So where this this A Ai's and Bi's, so that this lie in S union S inverse. So S is the generating set of the group G. So therefore, if I take this geodesic from 1 to U, the first edge will be labeled by A1, the second edge will be labeled by A2, and so on. And in the other direction, other end, so this geodesic joining G and UG, the first edge, so we will have an edge path. So the first edge will be labeled by B1, the second edge will be labeled by B2. Okay, got it. So now, so join this A1, A2, AI and this G, B1, B2, BI by a geodesic for I less than equals to this minimum of this N and M. So suppose this point is your A1, A2, AI, and this is your G, B1, B2, BI. So distance of this 1 to this A1, A2, AI. So this will be equal to I, and distance between G and G, B1, B2, BI. So this will be again exactly equal to your I. And note that because this U is equal to A1, A2, AM and B is equal to B1, B2, Bn. So I will be less than equals to minimum of this N and M. Okay. Now suppose, let us assume that this M is less than equals to N. So join this A1, AM to G, B1, Bm plus J by a geodesic. Yeah. So suppose we have something like this. And this part here, so it will be something like this. So here, if we have this to be my GB1 BM, so join this by geodesic and do it for all this M plus, so GB1 BM plus J. Okay, so this part is clear. Now let us take, so let GT be a vertex in this geodesic joining 1 to G such that distance between 1 to GT is equal to T. And then distance between U and UGT, so that will be also equal to your T. So here, if I take any element GT here, in this geodesic joining 1 and G, so this distance between 1 and GT will be same as the distance between U and UGT. Okay. So now observe the following thing. So now we are applying the exercise given in the last class. So distance between, so GT and GT prime is less than equals to K delta, where this GT prime, it belongs to your, the geodesic joining A1 and GB1, and distance between A1 and GT prime is equal to T. So if I take some point here, so if I take some point GT prime here, and this vertex will be your A1, So distance between A1 and GT prime, so this is exactly equal to T, which is equal to distance between 1 and GT. So if I take this two geodesics, so the geodesic joining 1 and G, this one, and if I take this geodesic joining A1 and this B1G, so the distance between GT and GT prime will be less than equals to K delta, where this K delta is coming from this exercise. So K delta is equal to 4 delta plus 3. So distance between GT and GT prime, so this will be less than equals to K delta. So this is clear from the exercise. Yeah. So now we continue this process for all geodesics joining this A1, A2, AI and G, B1, B2, BI. Sorry. So we continue this process for all geodesics joining A1, A2, AI, G, B1, B2, BI and the geodesic joining this U and G, B1, BMJ. So we continue this process and let us take this n to be equal to K delta times maximum of the distance between 1 to U and distance between 1 to B. So then, so what we have seen, the distance between GT and UGT, so this will be less than equals to K delta times maximum of distance between 1 to U and 1 to B. Yeah. So if I take this GT here and we have this UGT here, so distance between this GT and UGT, so this will be less than equal to this n less than equals to this K delta plus K delta, like this it will go on, and that will be equal to n delta, where this n will be less than equals to maximum of distance between 1 to U and distance between G and UG. So which is nothing but distance between 1 and P. So let me repeat. So distance between GT and UGT, so that will be less than equals to this K delta plus K delta, it will go on. So this distance between GT and UGT will be less than equals to n K delta, where this n is less than equal to maximum of the distance between 1 to U and the distance between G and UG. So which is nothing but equal to the distance between 1 and P. Yeah. So we have this thing here. So distance between GT and UGT is less than equals to this thing. So therefore, distance between 1 to this conjugate GT inverse UGT is less than equals to n. Where this n is, so here I have taken this n to be equal to K delta times maximum of this distance between 1 to U and 1 to B. Okay. So now what do you want? So we want an element x such that the distance between 1 to x will be less than equals to mu times the maximum of the distance between 1u and 1p. So this we want. So length of this x to be uniformly bounded in terms of this hyperbolic constant of g and the distance between 1u and distance between 1p. So we want such an x. To get such an x, so what we'll do? So we'll construct another finite graph, which is as follows. So let us take Bn to be the set of all words of length less than equals to n. Now construct a finite graph Gn with vertex set as Bn, and two vertices B1, B2 have an edge if this B2 is equal to A inverse B1A for some generator A, for some A which belongs to S union S inverse. So where S is the generating set of G. So B2 is equal to A inverse B1A. So either A or A inverse is the generator of this G, group G. So now observe this thing. If I take two vertices in this graph, so they are conjugate to each other if and only if U and V, so they lie in same path component of this graph Gn. So that part is clear. So if you have an path between U and V, so they are conjugate to each other. So that part is clear from the definition of this graph. And because this is a finite graph, so this has at most this number of vertices. So 2 times this cardinality of this S to the power n. So this graph has this many vertices. And now if I take any injective path in this graph, so this will have length at most this number, at most 2 times cardinality of S to the power n. So this will, so an injective path has length at most this thing. So any injective path has is a bounded length. So thus if I take any two elements which are conjugate in G, so they will lie in a path component. So U and V, so if they are conjugate in G, so this will imply that, so there exists a word W of length less than equals to 2 times mod of S equal to the power n, where n is equal to k delta times maximum distance between 1 to U and distance between 1 to V. Yeah. So this will imply that, this U and V are conjugate to each other, and so this W inverse U W will be equal to your V, and length of this word W is less than equals to this thing. And if I take mu to be equal to 2 times mod of S to the power k delta, so then we have this required result. Okay. So now using this thing, so we'll prove that centralizer of an element of a hyperbolic group is quasi-convex. So let us start with a hyperbolic group G, and now CG, it will denote the centralizer of the element G. So we'll prove that the centralizer is a quasi-convex, and this quasi-convexity constant, it will depend only on the length of G and the hyperbolic constant of the group G. Okay. Now let us take an element H in the centralizer of this element G. So because H belongs to the centralizer of G, so GH G inverse equal to H. And we have this following picture here. So first join 1 to H by a geodesic, and join 1 to G by a geodesic, and join H to GH again by a geodesic, and note that GH is equal to HG. So this length of this geodesic will be same as the length of this geodesic joining 1 to G. Okay. Now consider the geodesics 1H and GGH. So consider these two geodesics. So they are at distance 1G, distance apart. So what does it mean? So if I take the endpoints of those two geodesics, so this geodesic and this geodesic we are taking, so their endpoints are distance 1 to G apart. So distance between H and GH, which is equal to distance between H and HG. So again, it is equal to the distance between 1 and G. So therefore, the geodesics are distance 1 to G, distance apart. Now let us take a point HT in the geodesic joining 1 to H, such that distance between 1 to HT is equal to T. And if I take this point GHT, so distance between GGHT, which is equal to distance between 1HT, that is equal to your T. So HT, I have taken this point to be here, and GHT will lie in this geodesic. So distance between G and GHT is equal to distance between 1HT. And now if I join this HT and GHT by a geodesic, G prime. So G prime is nothing but equal to HT inverse GHT. So G prime is a geodesic word represent joining this HT and GHT. So G prime is equal to HT inverse GHT. So this will imply that G prime is conjugate to G. So now by the previous lemma, so there exists a word X such that XG inverse is equal to G prime, and distance between 1x is less than equals to mu to the power maximum of the distance between 1 to G and 1 to G prime. So this mu, it depends only upon this delta. And now observe that distance between 1 to G prime is less than equals to K delta times maximum of the distance between 1 to G and distance between H to HG. So again, this is coming from the previous lemma. So this distance, so distance between HT and GHT, so that will be less than equals to K delta times maximum of the distance between 1 to G and distance between H to GH. And distance between HT to distance between, distance between HT to GHT, it is nothing but it is the distance equal to distance between 1 and G prime. So that is the thing I have written here. Yeah. So distance 1 to G prime is less than equals to K delta times maximum of these two distances. And distance 1 to G is same as the distance between H and HG. So this is equal to K delta times distance between 1G. So from this inequality, so distance between 1 and x is less than equals to mu to the power K delta times distance between 1 and G. Okay. So we want to prove that the centralizer is quasi-convex. So we have taken this point HT, and we need to find some point in the centralizer such that the distance of HT to that point is less than equals to some function of delta and the length of G that we want to show. So we'll show that this HTX, so this in fact it lies in the centralizer. And we know that this length of this X is bounded in terms of the hyperbolicity constant and the length of G. So claim is HTX, it belongs to the centralizer of the element G. So HTXG, so which is equal to HT G prime X so because this xg, so this is equal to G prime X from here. So xg is equal to G prime X. So we put this thing here. So HTXG is equal to HTG prime X, and HTG prime is again equal to GHT because G prime is equal to HT inverse GHT. So because of that, so what we have, HTXG is equal to GHTX. So this proves that this HTX, it belongs to the centralizer, and distance between HT and HTX is less than equals to mu to the power k delta times distance between 1 and G. And this is true for all HT belongs to this belonging to this geodesic joining 1 to H, and H belongs to this centralizer. So therefore, so this centralizer is a quasi-convex subgroup. Okay, so we'll stop here. In the next class, we'll prove that intersection of two quasi-convex subgroups is again a quasi-convex subgroups.